Hey guys, my name is Lucas, and in this video I'm going to show you what I've done in my free time over the last 3 years. It's a really cool project, so stay tuned. Thank you.
Okay, to be honest, that is a bit too fast. I am a guy from southern Germany, and well, yeah, my name is Lucas, and that is correct. And it is also correct that my never-ending project, which consists out of building an electric jet board, has been going on for more than 3 years so far. But there's way more to the whole story, which I just don't want to forget over time. Making videos about the project will help me to remember in a few years. That is big enough of a reason for me to invest some extra time. Now, whether the project is cool or not, you can of course decide yourself. I hope you'll enjoy. There's one more thing. If you're not really interested in all the theory behind water jets and how to analyze them with software, then just skip the part from minute 3 to minute 9. Now, let's dive right in without further talking. To give you an introduction into what I am doing, how the project looks and how it works, we can have a look over the almost finished CAD models. What you can see on your screen right now is basically everything. This is how the finished product is going to look, or at least close to it. Having detailed CAD models really helps with working effectively. CAD models are accurate, and you always have a digital twin to compare your real work with. They also open up a path to relatively quick manufacturing by extracting data to my 3D printers or CNC machine. But I'm going to talk about CAD construction and manufacturing in the future. Let's look at the actual topic of the video now, the propulsion unit of the surfboard. The project uses the axial jet pump you can see on your screen as its propulsion unit. Such a jet pump just works like other pumps do when we only look at the basic principle. A liquid is pulled in at one side and later on ejected or pressurized at the other side. Of course, there are many different technical concepts of liquid pumps which all lead to different specs, but the original use case is moving a liquid by increasing pressure. To experience this a little closer, we can have a look at a cross-sectional view of the axial jet pump. A jet pump can be divided into 4 main parts. The intake, which leads the flow into the pump. The impeller, which accelerates the flow through its rotation. The stator, which straightens the flow to make the waterjet more efficient and holds the main bearing. And the nozzle, which compresses the flow to make it faster and give it more power. When the surfboard sits in the water, the jet intake is partly submerged. Through spinning up the impeller, a suction is created, which pulls the water in. Like that, the water gets accelerated. Then, after passing the sucking impeller, which adds a little bit of a swirl to the stream, the water is straightened by the stator and pushed out through the nozzle. At that point, we can see why this pump is an axial pump. The water is moving parallel to the rotating power transmission shaft. That is not the case with radial water pumps. But why is it possible to propel a whole surfboard with a surfer on top by just shooting out water at the back? To understand that, we can have a look at basic physics. What we must look at is Newton's third law. For every action, there is an equal and opposite reaction. Water that flows with a certain velocity and mass flow rate always exerts a force. This force has its equal and opposite counterpart. Because of that, we can propel objects by shooting out particles. Rockets, planes, and lots of other vehicles use that effect. If we want to write down an equation for the thrust force of the jet, we can simply multiply the mass flow with the jet outflow velocity. If the board is moving already, we have to also consider the board's speed. The reason for using an axial pump to propel the surfboard or other quick boats is that axial pumps are efficient when it comes to moving large volumes of water at high speeds and relatively low pressures. Large volumes and high water speeds result in a higher propulsion force. Using waterjet propulsion for slow water vehicles is relatively inefficient, which is why you mostly see waterjets on speedboats or jet skis. This is a simple formula that displays the efficiency of a waterjet at a certain speed of the propelled vehicle. It tells you how much of the mechanical energy from the motor is converted into the kinetic energy that we want. An important fact is that small waterjets in the 10 to 15 kilowatt range can reach efficiencies of up to 60%. Bigger waterjets for ships can even reach efficiencies of up to 70%. But now, when we take the formulas that I have shown you, we can see that most of the quantities aren't clear when we don't have a waterjet yet and start at zero. How do we design a jet that puts out a certain amount of force? And how do we find out the properties that our design would have without building a very complicated testing rig? The answer to those questions is called CFD, Computational Fluid Dynamics. With CFD, you can simulate the flow through geometries and extract all the physical quantities that you want to know. It is an iterative process because between each simulation you can adjust your geometries to make your design more efficient. CFD always starts with the meshing process. That means that the body that is going to be analyzed is split up into lots of little cells. Those cells are where the magic happens. To simulate a flow accurately, we need lots of mathematics. The base for simulating fluids are the Navier-Stokes equations in combination with continuity and energy equations. Those equations can describe every cell. Like that, the whole system can be described. All of the math of every cell combined results in gigantic systems of equations, which are then solved numerically to get the flow values for every cell. Solving numerically means that solutions are approximated instead of found analytically. The mesh is defined by the user, which means that you can set the framework in which the equations are solved by yourself. There are lots of mesh types like tetrahedrons, hexahedrons, and more forms of polyhedrons. After meshing the system, you set up your CFD simulation. Important boundary conditions are set. You, as the user, define where fluid flows in and out of the system, how fast it is, and which mass flow rate or pressure it has. After setting all the constraints, solving can be started. Solving is an iterative process that takes time and computing power. With every solve iteration, the searched values gain accuracy. After the user is satisfied with the convergence of the interesting variables, the solving process is stopped. Then we go into post-processing. Post-processing is the process step where the simulation outcome can be visualized. Lots of parameters can be viewed. While post-processing, you decide what needs to be changed within your geometries to make your construction more efficient. After changing your geometry, everything starts again. My waterjet for the surfboard took about 300 iterations to get me happy. I've reached an efficiency of 57%, which is right in the earlier mentioned sweet spot for a small waterjet. I also simulated the water resistance that the surfboard has to overcome at a certain speed. Like that, I could see if my jet generates enough force to bring the board up to the desired speed. But, to be honest, let's finally get a bit more practical now. What I can offer is a Buildlapse of the finished propulsion unit of the surfboard. What you saw in that Buildlapse was the assembling process of the jet. But it is more important that I don't forget mentioning the production of all those parts, because that was way more time consuming. Some of the parts I milled at home on my CNC, some others I turned and milled manually, some are 3D printed, and some more are produced by friends. Having the right contacts and friends is so incredibly important. The impeller, the stator, and the nozzle, for example, are laser sintered and consist out of automotive grade aluminium. It is basically impossible to get such parts for almost nothing without knowing the right people. What you see on your screen is my old and trusty testing stand. It works quite well, as you can see here. And it also works well with the finished propulsion unit of the surfboard. The main purpose of the testing stand is measuring thrust. It does that through a crane scale that is connected to a motion-free sled guided by rolls. The jet sits in the sled and pushes back. The pushing force is then displayed on the little screen of the scale. That enables me to record all the values and analyze them later. To demonstrate the setup to you, I bought this pool on eBay. Putting the testing stand in the pool and securing it with about 250 kilograms of stone should work just fine. The big weight is needed to keep the stand secured properly. Without the weight, the whole assembly would move and probably rip the pool apart. And now, I can finally show you the performance of the jet. Now, what you just saw there was the jet running at about 5 kilowatts of constant power. In that state, the jet creates about 45 kilograms or 450 newtons of thrust. The maximum continuous power this system will be running at is about 10 to 11 kilowatts, but to be honest, Testing that in the pool is not the best idea, so you'll sadly have to wait for the next videos. What I just did there was measuring all the important temperatures by hand to see if my components stay cool. I don't have to do that because my temperature sensors tell me the same values, but I still do it because I once had a sensor problem which led to a burnt motor. Cooling is a very important factor for the whole system. If all of the power electronics and the motor leave their working temperature ranges, we just have a system that is not resilient and destroys itself quickly. Keeping temperatures under control is very important. With Waterjet Propulsion, it is very easy to get a high pressure water stream through separate outlets at the nozzle. Because of that, all the important components of the board, except for a battery, are cooled by water that flows through them. The two additional water streams that you see next to the main propulsion stream are the two water cooling outlets. The water that is coming out already found its way through the whole system. At the day at which I recorded the footage that you see right now, we had about 7 degrees Celsius. To my surprise, the motor temperature didn't even climb above 30 degrees Celsius, although it did run long. That is a good sign. What you see on the laptop behind me is the monitoring software that I use to track all the values that I want to know. The software communicates with the motor controller and gives me insights into every important detail. After each run, I can read out all the values and save them into an Excel sheet to analyze them later. Like that, it was possible to get the system to where it is right now. It makes me happy that the propulsion unit of the surfboard is performing like it should now. Of course, there are always things to optimize, but right now I am relatively confident that the jet board will work nicely, and that's the most important thing. You'll find out if the board works like it should in the next videos.
There I am again. What you just saw was the first video of a series of about 4 to 5 videos in which I am going to explain almost everything about the electric jet board. This is my first such video, so if you have any tips or tricks that you would like to share with me, then please feel free to do that. I would like to make my videos better. Yeah, that's the whole point.
Before I end the video, I want to thank all the people who helped me on the way to a well-functioning jet. Without some of the parts or services that I basically got for free, nothing would work like it should. Also a big thanks to my dad, who is the other dude who was running around in the video. If you liked what you just saw, feel free to like the video and maybe even subscribe to my little channel. And now,
thank you very much for watching. Have a nice time. Bye bye.